those two surveys using optical telescopes on the ground, using images taken through the Sloan filter system, which is now the standard for us in astronomy. And by choosing the right colors of the objects, we can eliminate the ones that are very relatively close to us. So we only come to the telescope and look at the distant galaxies we need. So there's a lot of collaboration gone on with these international teams, helping us set up the project before we even come to our own Anglo-Australian Telescope for the final stage of the measurements.
Right, so I guess that would take quite a while just to set the project up, as you say.
Well, this has been unusual for me. Normally I've done smaller projects and you might spend a few months talking to people and then meet them a few months later. This project probably took about 2 years of setting up and even some financial investment just to set it up, because a team of us had to go to Pasadena in California to meet the leaders of the GALEX team to make a case as to why they should give us some of their data and even devote some of their telescope time, their satellite time, to our project. Since we weren't able to pay them directly for it, they had to do it with their own funding.
Oh, obviously they gave in.
Yes.
Okay, so that's cool. So basically, now you've got to the end of the project. There are other projects that are in your wake or possibly at your side. One of them being BOSS, the Baryon Oscillation Spectroscopic Survey. How does that sort of fit in with WiggleZ?
So BOSS is a very similar project. It's actually run by the people doing the Sloan Sky Survey, and what they're going to do is devote a very large amount of time on the Sloan telescope to do a similar experiment over probably a larger volume of sky than us, and they will, now they've got the technology to do this, a similar experiment. They can, probably in a few years' time, we'll have done a better one. The main difference there is they're looking at a bigger volume of space, sort of similar distances, maybe a little bit further, and whereas we will just be able to detect the wiggles, they will be able to measure them in exquisite detail and get a much more accurate signal. But we will be the first to find the wiggles, and they'll be the ones who follow up with the high resolution, much more fine detail measurement that will just improve on the result.
Okay.
So that's one of the coming projects.
Okay, and what sort of duration would that project run for? When would their results be expected to come out?
These things are always very hard to predict. In principle, they could be getting results out in a year because they'll be collecting galaxies at a faster rate than us, since they basically have their telescope 100% of the time. However, there are always enormous complexities in analyzing this sort of data, so I would guess more like 2 to 3 years.
Okay, and so you won't. There's no plans to actually lend them our spectrograph. Is that right?
No, but we have exported this sort of technology to one of the big telescopes in Hawaii. The Subaru telescope in the Japanese 8-meter telescope in Hawaii has a similar spectrograph with optical fibers, but a faster positioning system built by Australia. And one of my colleagues from Swinburne University, Carl Glazebrook, is working on a project to do a similar experiment to ours, but with much more distant galaxies, taking the same idea but moving further away. Now, in principle, we don't actually expect dark energy to have so much effect earlier in the universe. The idea here is that if dark energy is constant, then as the universe expands, gravity, when the universe was smaller, gravity was very powerful because things were close to each other. But as the universe expands, the effect of gravity gradually weakens as things are further apart. So initially, the universe was slowing down because gravity was so strong. But if dark energy is constant, then over time, as the universe expands, dark energy remains constant, but eventually gravity gets weaker, and then dark energy wins and makes things go faster. Now, We think that happened about 5 to 10 billion years ago. So only in the recent half of the universe is dark energy winning and making it expand faster. These coming experiments will be looking back before dark energy was thought to be winning. So we don't expect to see dark energy having such an effect then. But that's just our theory. We need to check. So these experiments are necessary. They're going to go further back in time and see if, as we thought, back in time, gravity was winning and not dark energy. Well, and there's another Australian project thinking of doing a variation on that using very distant, the most distant, the brightest galaxies called quasars, to sample the material in between by, you can see when the light from the distant galaxies has gone through a gas cloud. And that's another experiment, again, to try and measure dark energy. Just check that further back in the universe, gravity was winning, not dark energy. So those are two experiments also coming up in the next probably 2 to 4 years.
It sounds to me like that's a very good case for extra funding.
Yes.
Obviously before the universe goes poof. So I guess once expansion goes on for the next X billion years, the effects of gravity become weaker and weaker, and then I guess we just become invisible after a while. I mean, what's the current theory on what happens after, if you double the age of the universe?
If you double the age of the universe, what you're going to see is, on average, everything getting spread pretty thinly. But on the small scales, gravity still wins, in that it's not likely to, on that sort of time scale, pull galaxies apart. They've already pulled themselves together with their gravity, and their neighboring galaxies they're stuck in together. So they will stay together, but the distances between the galaxies, between the groups of galaxies, will increase and increase and increase.
Well, I'm pretty sure that we haven't heard the last of some speculative theories out there, and I look forward to actually getting old with those later on. But interestingly, what's your next project? As this one's coming to an end, what do you have in mind? Anything in the sights?
My current interest is actually almost at the other end of the universe. I'm now focusing on one of my earlier labs, which is very small galaxies. We actually, again, in a different project with this very same telescope, we discovered a new type of very small galaxy about 10 years ago. And we've been trying to see how we can use these small galaxies as a bit like archaeological remnants or forensic evidence to help study how galaxies themselves were assembled. And currently I'm working with some colleagues in the UK on analyzing some theoretical models of how galaxies form, particularly how our own Milky Way galaxy formed, to see where, if we can pin down in the theoretical numerical computer models where these objects came from, then we can compare that with where they are in the actual universe to test our models of how the galaxies formed. So this is a mixture of observing a new type of unusual, very small galaxy and then building up the theoretical predictions with my colleagues who are much more expert in the computer models until we can merge the two and try and start answering details of this question of how do galaxies actually form. So very small scales compared to the WiggleZ project, but another aspect of looking at the history of where we came from.
Right. Each journey, even a long one, begins with a small step, right?
Yes, yes.
So I guess that means that you have to work with, let me see, theorists, observational astronomers and theorists. That's a strange beast, huh?
Yeah, and it's getting them to talk the same language where they actually come together and compare the results is the real challenge. If you have a computer model, it has neither the observational data nor the computer models are perfect. And you've got to understand the imperfections of both before you can come up with something from each side that you can compare honestly. And my colleague I work most with in the University of Sussex, Peter Thomas, is very good at keeping me honest. And he actually makes me understand what he's doing. He tries to understand what I'm doing. And we try and